All right, so our last section of chapter 4 is still on solving systems of linear equations, but now we're going to be solving them by our last method, which is elimination, and you'll sometimes hear it called addition. Both of them kind of speak to what we're doing. We're eliminating one of the variables by adding the two equations together. And so after this, we have 2 more chapters, so we're almost done. Chapter 5 is a little bit longer. But yeah, two more chapters and we're done. So let's go ahead and with elimination, I want to go straight into some examples. This one's definitely a lot easier to learn. Instead of writing out all the steps, just jumping straight into some examples and seeing how it works. So for these examples, we're told to solve by elimination. And again, on a test, it'll probably say solve by elimination or substitution. So we'll talk about kind of when you should use one versus the other when we look at some of these today. We saw in some of them yesterday when it was just a variable by itself. So if you started with something like y equals whatever it was in your other equation, if you have one of those variables already by itself, this is a great time to use substitution. Or if you have a variable that doesn't have a coefficient, but it's easy to solve for, substitution's still really good there. The time when you're not going to want to use substitution is in some of these that we're going to see here, when maybe all of your variables have a coefficient that's not 1, and it's not going to be nice to solve for one of the variables and plug into the other equation. So number 1, we're given x plus y equals 8 and x minus y equals 2. So now this one's set up pretty nicely for both equations. The first equation, if you notice, is pretty nice to solve for either x or y. So that makes substitution really nice for this one. But elimination is even nicer, because what we're looking for in elimination is we want 2 of our coefficients on both the x's or both the y's to be opposites of each other. And so our x's both have a 1, but our y's have a 1 and a -1, which makes them opposites. If you remember, when we add opposites together, we get 0. So that's how we're going to eliminate one of our variables here. So let's go ahead, and what we're going to do is we're just going to add these 2 equations together, which means you always want your like terms to be lined up. So x's, y's, constant on the right side. If they're not lined up and on the correct side, you're going to have to just rearrange it. It's usually given to you like this, but we'll see one where you might have to rearrange it. So if I add straight down x plus x, remember 1x plus 1x is 2x. Y plus a -y, those cancel out or eliminate. Bring down the equal sign, 8 plus 2 is 10. Now we have a nice equation with one variable, and all we have to do is solve this for x. So if we divide both sides by 2, we get x equals 5. And remember, we still need both the x and the y's together as part of our solution. So I'm going to take this 5 for x and plug it back into either one of our equations. The one with the positive y is going to be a little bit nicer. So we have x plus y equals 8. We'll plug in 5 for x. So 5 plus y equals 8. And subtract that 5. So we get y equals 3. And we have our solution. Remember, write it as an ordered pair. We have the solution 5, 3. So a lot of the time, if it's set up really nicely for elimination, you notice you have opposite coefficients. This way is actually a little bit faster than substitution, but sometimes it's just a matter of personal preference, which one you like better. So let's go ahead and try a couple of these that might be a little bit trickier than this one. So this one was set up pretty nicely. For this next one, we want to make sure the equations are in standard form. And so remember, standard form is ax plus by equals c, which is the form that these guys were in up here. We had the x and the y on the left, constant on the right. It technically doesn't matter if it's not in standard form, as long as you make sure that your x, your y, and your constant are lined up and they're on the correct side. So if I have the x and the y and the constant all lined up, but the equal sign is in between the y on one equation and after the y on the other, that doesn't work. So your addition or subtraction, equal sign, and then your x, your y, and your constant all have to line up. That's kind of the big important thing here. If you can, I would just always have it standard form. It's just kind of a nice habit to get into. So let's go ahead and try one of these. We'll start a new page here just so we have, yeah, so we have plenty of room. Number 2. All right, so this one we're given negative 5y equals negative 8x plus 32. And let me fix this really fast. There we go. And our second equation is 4 equals 4x plus 5y. All right, so if we go ahead and look at both of these, neither one of them are in standard form. The second one is pretty close. If you notice, the x and the y on the right, constants on the left. So in order to get this in the right form, what we can do is just kind of flip this guy around, because if we had 2 equals 2, we flip that around, it's still equal, it's not going to change it. So let's go ahead and flip our equation around. So we have 4x plus 5y equals 4. That one was super easy to take care of. This other one here, I'm going to go ahead and rewrite it down here, and then we'll rearrange it. So let's go ahead and add 8x to both sides, just so we get the x and the y on the left, constant on the right. So we have 8x minus 5y equals 32. And now this one is in standard form, so we can take it and put it back up here. All right, so now we have our new system, these two equations right here. And so what we want to do here is, again, check to see if we have opposite coefficients on the x's or the y's, which we do. The x's are an 8 and a 4, they're not even the same number. But on the y's, we have negative 5 and 5. It doesn't matter which one's negative, which one's positive, as long as they're opposites. And so this one's set up perfectly for elimination. And let's say you were given this on the exam, and it told you to use substitution or elimination. Because it's set up so nicely for elimination, it's definitely a better option to use elimination. If we were to try to use substitution, solving for x or for y in either one of these is going to give us fractions. So we want to avoid those fractions at all costs. So elimination is definitely the way to go. So let's go ahead and add these equations together. So 8x plus 4x is 12x. These y's cancel out or eliminate. 32 plus 4 is 36. And now let's divide both sides by 12. And we get x equals 3, which is, remember, part of our solution. Now we want to plug this back in to find y. It can go back into either of the equations you started with or either of them in standard form. There isn't really a best option in this one. The original one where y is on the left by itself, almost by itself, is going to be the best option here. It's not a ton better than the other options, but since we're solving for y, this one is almost by itself, so it's going to have the least amount of work. So I'll go ahead and just plug it into this first one, that's negative 5y equals negative 8x. plus 32. So if I plug in x, we have negative 5y equals negative 8 times 3 plus 32. And now simplify the right side more. So negative 5y equals negative 24 plus 32. Combine again, so negative 5y equals positive 8. And divide both sides by negative 5. And this one does give us a fraction answer, which is perfectly fine. We get negative 8/5. So our answer as an ordered pair is the point 3, negative 8/5. And this is another one of those that shows why graphing isn't a good option. If we would have graphed both of these equations, first of all, they're pretty ugly equations to graph in the first place. And when we graph it, the x might have been pretty okay to see, the 3, but getting negative 8/5 from a graph is pretty tricky. So elimination and substitution are a lot better than graphing when it comes to accuracy with fractions. All right, let's try another one. So in these past two examples, we've kind of had nice examples where once it's all rearranged, we've had opposites for the y's or the x's. Remember, it doesn't have to be one or the other. Now let's take a look at one where we might have to do a little bit of manipulation. So this one we're given 4x minus 3y equals 6, and 2x minus 7y equals negative 8. All right, so again, what we're looking for is opposites. We have 4 and 2 for the x's, negative 3 and negative 7 for the y's. None of those are even the same number. So first thing you want to do is figure out which variable would be easier to eliminate. And sometimes there isn't a right or wrong answer. In this one, there's one that's a little bit easier. So if you notice 4 and 2, so what we're going to be doing is multiplying these equations by a number so that they look the same, or they look like they're opposites of each other. I can turn a 2 into a 4 by multiplying it by 2. And that's all I would have to do here, a negative 2 so that they're opposites. With the y's, 3 and 7, the least common multiple for those two is 21. So I'd have to multiply this 3 by 7 and the 7 by 3, so we'd be doing something twice. So if I can avoid doing something twice, I'm going to, and I'm going to go ahead and just focus on the x's. So remember, what we want is opposites. So I want to multiply, and it has to be the entire equation because we don't want to change the equality. I want this to be a negative 4, so I'm going to multiply this by negative 2. And it's going to get distributed to every single one of those terms. And then I'm just going to rewrite both equations off to the right side so they're still lined up. Top one's not changing, so 4x minus 3y equals 6. Bottom one is going to become negative 4x. Negative 2 times negative 7 is positive 14y equals negative 2 times negative 8 is 16. Always double check to make sure you multiplied every single term by the 2. A lot of the times people will forget to multiply the right side. That's why I like to just put parentheses around the entire equation so you don't forget to multiply it by the right side of the equation. All right, let me just write a little note here. We need opposites. Okay, so let's go ahead and add these two equations together. 4x and negative 4x, now the x's cancel. Negative 3 plus 14 is 11y equals 16 plus 6 is 22. Divide both sides by 11 and we get y equals 2. So we have part of our solution. And now we can go ahead and take this and plug it back into either equation. They're both kind of ugly to work with. We've got a negative 3y and a 7y. I'll just plug it into the first one because that 3 is smaller. But again, either one works. So we have 4x minus 3y equals 6. And we'll go ahead and plug our y in. So 4x minus 3 times 2 equals 6. Simplify, so 4x minus 6 equals 6. Add that 6 to both sides. So we get 4x equals 12. And divide both sides by 4. So x equals 3. And so we have our solution, 3, 2. All right, so let's go ahead and try one more example like this. I would suggest doing this one by yourself first and then checking your answer if you feel comfortable doing these now. It's going to be pretty similar to the last one. So this one we're given 2x plus 3y equals negative 15 and 5x plus 2y equals 1. All right, so again, checking for opposites. 2 and 5, not opposites. 3 and 2, not opposites. So we are going to have to multiply these by something in order to get opposites. And so if we look at these, I can't turn a 2 into a 5 without introducing fractions. Because multiplying by 2 gets me to 4, multiplying by 3 gets me to 6. Same thing here, I can't turn a 2 into a 3 without bringing in fractions. So in order to avoid multiplying by fractions, I'm going to go ahead and multiply both equations by something. And it doesn't matter which variable you pick, especially with these numbers. 2 and 3 are both pretty close, 2 and 5. Their least common multiple is also pretty small. Let's go ahead and do the y's though. So think the smallest number that 2 and 3 both go into is 6. So our goal is to make one of them a 6, one of them a negative 6. And now it doesn't matter which one you pick for which. I'm going to go ahead and we'll make the first one positive 6, the second one negative 6. So I need to multiply 3 by 2 to get to 6. And remember, we're distributing that to every single term. And then to make this 2 into a negative 6, we need to multiply it by negative 3. So for these, think just like getting a common denominator. You have to change the entire fraction. Same thing here, we have to change the entire equations. And so we'll distribute this to the entire equation here. And then again, I'll rewrite them off to the right. So we get 4x plus 6y equals negative 30. And then negative 15x, negative 6y equals negative 3. And now let's add these together. So 4x plus a negative 15x gives us negative 11x. Y's cancel. Negative 30 plus negative 3 is negative 33. Divide both sides by negative 11. And we get x equals positive 3. So then again, let's plug it back into one of our equations. Doesn't matter which one. I'm not going to do it to these two, the ones that we changed them into, just because these numbers are bigger. You still could, but I like to work with smaller numbers when possible. So I'm going to go ahead and plug it into the second one, just because the numbers are a little bit smaller. So we have 5x plus 2y equals 1. 5x, so 5 times 3 plus 2y equals 1. 15 plus 2y equals 1. Subtract 15, and we get 2y equals negative 14, and divide both sides by 2, so we get y equals negative 7. And so our solution is 3, negative 7. Another thing to note here is that you can still check your solutions with these, just like we did in the graphing and substitution sections. You're just going to take this point that we got, the 3, negative 7, plug it back into the two equations you started with, and make sure that they both give true statements. If one of them does not, then you went somewhere wrong in the solving, or maybe when you plugged it into check, you did your arithmetic wrong. So always double check your arithmetic in the check too. All right, now we're gonna do two last examples, and these are the special case examples. They work pretty similarly to the ones in the substitution section. So we're looking for similar things when we're looking for those two special cases. So number 5, we're given 4x plus 3y equals 10, and 2x plus 3/2 y equals 12. Now, a couple things to note here. We don't have opposites on the x's or the y's, so we know we're gonna have to make them into opposites. We also have a fraction down here on the y term. So first thing I'm gonna actually do is get rid of that fraction. So I'm gonna go ahead and multiply the second equation by 2. And now if I go ahead and do that, 2 times 2x is 4x. 2 times 3/2, if I multiply this down here, those 2's cancel, so we get 3, so plus 3y equals 2 times 12 is 24. And then I'll go ahead and bring over that first equation just so they're lined up. Oops. And if you notice, the x's and the y's both have the same numbers, but they're not opposites. So we do want to go ahead and change the signs. So instead of multiplying this bottom equation by a 2, I could have multiplied it by a negative 2, and it would have given us the opposite for each of the x's and the y's. So instead of a 4x, we want a negative 4x. This 3y would become negative 3y, and negative 2 times 12 is negative 24. Now that we have opposites, let's go ahead and add these two equations. 4x and negative 4x cancel. 3y and negative 3y cancel. I can't just leave the left side with nothing there, so remember opposites add to 0. 10 plus negative 24, negative 14. So anytime this happens, all of your variables disappear. It depends on what kind of statement we get. So if we end up with a false statement like this, what kind of solution do we get? Well, we get no solution. And remember, the other way of writing this is that empty set. So either way, I think the empty set is what they'll use on the homework, but I'm not 100% sure. But think, false statement, no solution. And now let's go ahead and look at that last example, number 6. Just to see what the other special case is going to look like. 4x minus 6y equals 10, and negative 10x plus 15y equals negative 25. All right, so let's go ahead and take a look at our numbers here and see what Coefficients we can change to make them opposites. 6 and 15 both go into 30. That's getting a little big. 4 and 10 both go into 20. So I'm going to go ahead and change the x's. And so we already have a positive and a negative, so we don't have to worry about the sign. So let's just focus on what we need to multiply them by. 4 has to be multiplied by 5 to get to 20. And 10 has to be multiplied by 2. And then we'll distribute that incompletely and write our new equations. So 5 times 4x is 20x. 5 times negative 6y is negative 30y. 5 times 10 is 50. And our second equation, 2 times negative 10 is negative 20x. 2 times 15y is positive 30y. And 2 times negative 25 is negative 50. So anytime you have these special cases, you should always notice something happening kind of weird when you go to add the equations. So just like last time, if you notice the x's cancel out and the y's cancel out. So on the left side here, our opposites add up to 0. And if we look at the right side, 50 plus negative 50 also gives us 0. So since this statement is always true, then this one, there's a couple ways to write the answers here. We can write an infinite number of solutions. So remember, that means if you have the exact same line, they're always touching, so you have an infinite number of solutions. They all relate back to each other. If we look back to number 5, this one here, since we had no solution, what kind of lines must we have? Parallel lines. Since they have no solution, they never touch. And then finally on this last one, it might say an infinite number of solutions. It might also say all real numbers or use this symbol. So I'm going to put this here just in case you end up seeing this. Or if you look up other help videos online, sometimes they use different answers, but these all mean the same thing. They just mean that all of the numbers on the number line are a solution to the system. All right, so that's it for chapter 4. Next time we'll start looking at exponents, which is pretty much what all of chapter 5 is going to be about. And then we'll start talking about polynomials and how exponents come into play with those.